Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Exponential Function Basics, Concept number 5, Exponential Decay Function. All right, so the odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. What we're doing here is effective. I'm coaching you to turn your wants and desires of getting an A or perfect test scores into a new paradigm. I want to include everyone who needs a boost in Algebra 2. And if I could stick every single math student with a syringe containing a healthy dose of eye-opening awareness of their inner mathematical genius, I probably would. So inbox me at memedicine@gmail.com to get your healthy dose by ordering and purchasing the complete Algebra 2 Cram session beyond the series. All right, so let's delve into the question. Okay. For the exponential function y equals b to the x, draw a decay curve. Definitely press pause if you need to, and I'll give you a moment to think. All right, so hopefully by now you are able to arrive at an answer, and if not, that's completely fine. Let's tackle this riddle together. In the general format of the exponential function y equals b to the x, remember that the format is a constant raised to the independent variable x, okay? And not the other way around, not x raised to some number. All right, so we have our constant b, or the base. We have our exponent x, and we have the result, or dependent variable, our power y. Sometimes there's a bit of misnomering going on, and the exponent is referred to as the power, but that's wrong. It's erroneous. Let's say that x were given a value of 2. So b to the second power would be equivalent to what? I mean, b raised to 2 would be equal to y, not b to the second power. We would say that y is the second power of the base b in the event that the exponent is 2. Okay? All right, so for the exponential function y equals b to the x, the shape of the graph depends on the value of the base b. So wherever b falls between 0 and 1, that means it's either a fractional number that's less than 1 but greater than 0. The shape of the curve is going to look like this. Here we have our y-intercept of 1, because any base raised to the 0 power when you input 0 for x is going to yield 1, regardless of the constant base, okay? And a visual inspection also reveals that we have a horizontal asymptote going on at y equals 0, all right, also known as the x-axis. Thus, the y, or the output or dependent variable, is decreasing from left to right, or decaying, okay? Always approaching but never touching the horizontal asymptote at y equals 0. So as the x input or independent variable increases, the y value is decreasing or decaying. And this is a classical exponential decay curve, okay? So this is our answer. But we're not finished just yet. I want to go over a few things with you. We're only concerned about positive b, so although the constant in this decay scenario is falling between 0 and 1, it's always going to be positive, or we're only selecting positive values. Let's say that we allowed b to be negative, which is what we don't want. Let's say we were to plug in a value of -2. Well, let's also say that, our function is between 0 and 1 and it has a fractional value of 1/2. This is what would happen. We would have to evaluate 2 to the 1/2 power. So we know that negative 2 to the 1/2 power, rather. We know that to evaluate this, we basically raise the base to the numerator and take the nth root of the denominator. So we're taking the square root or the second root here. And what we see is, in evaluating this, we have two interesting issues going on. First, when we separate this, because this is how you would evaluate it algebraically, we separate it into the negative portion and the positive aspect. So for the negative portion, you're going to have to evaluate the square root of -1, which is the imaginary number I, okay? And the square root of 2 is an irrational number. So we're dealing with an irrational number and an imaginary number. And when I say irrational, when you try to evaluate this square root, it's a decimal that continues on and on forever. It never terminates. So I think the value of the square root of 2 is like 1.41356 or something like that, okay? ... It goes on and on forever. So we don't want this. That's a no-no. And we don't want b to actually be 1. Although it can be less than 1, we don't ever want it to be 1. Because if b is equivalent to 1, this is what's going to happen. For any value of x from -infinity all the way up to infinity, you're just going to get 1. Okay, and the problem with this, because 1 raised to any power is just going to be 1. The issue with this is that if b is equivalent to 1, y equals b to the x is no longer a 1-to-1 function. Rather, it's a 1-to-many relation, and a horizontal line drawn for the horizontal line test would touch the curve at many places. And this means that the y equals b to the x relation would return the same output value of 1. So it would look like this. Pretend this line is straight. Or dependent variable for all the independent x variables input, okay? Yeah, so whether x is over here, if the base b were equivalent to 1, the answer would just be 1. And that's problematic, and we don't want that. Visual inspection, last but not least, also reveals that the domain, or all the x values that make this true, is basically going to be all real numbers, all the counting numbers on the number line. And the range, or the output values that make this curve true, is going to be anything bigger than the horizontal asymptote y equals 0, as you can see upon visual inspection. So this was not that bad. Intellectual comprehension of this material was not difficult at all. And after the short amount of time it takes to complete this entire cram session, which you're going to inbox me at memedicine@gmail.com for ordering and pricing instructions, you'll be prepared to answer a battery of questions about any Algebra 2 concept. So thanks for tuning in, and good luck studying.